Okay, so this is question 2 of the AQA Arrhenius questions. They're in the PowerPoint. I've scanned in a model answer, but sometimes obviously seeing it live kind of helps a bit more. So first of all then, you are asked to, you're given this equation, and a series of experiments have been carried out at a given temperature, and this is the rate equation. Okay, I'm just going to highlight the fact that h plus is to the power of 2 because it's easily missed, particularly as it's not there. So we've got an incomplete set of results. So at some point we're obviously going to need to finish that table, and you're asked to use the data from experiment 1 to calculate a value for the rate constant k. So we've already done this in question 1. We need to rearrange to give k equals rate over, and then BrO3, Br minus, and then H plus squared. So we then just need to plug in the rate, so 2.4 times 10 to the minus 2 divided by 0.1 times 0.2 times 0.3 squared, which is 0.09, and that should give you a value of, just checking here, yeah, appropriate number of significant figures is 2, so that should give you a value of 13. So that's going to get you 2 of the 3 marks, and then the final mark's going to come from the units. So we've got moles, dm minus 3, s minus 1, over, and then we've got a whole bunch of stuff down here. So we've got mole dm3, and we've got, what, 4 of those, so we can get rid of 1, 2, leaving us with 3 of them, and then say 1 over those 3, plus we've got that one, gives us moles to the minus 3, dm plus 9, s minus 1. Okay, part B, complete table 1. So we need to rearrange to find BrO3 minus. So we're going to say Br, is that still visible? Yeah, BrO3 minus equals rate over k, which we've now calculated, and it's a constant, it will be the same for all of them, times Br minus times H plus squared. And what's this for? So for experiment 2, so we're going to plug in all of those figures, remembering again we need to square that one. We've got the rate, we've got that, and we've calculated k, so that gives us for BrO3 minus a value of 0.15. It's going to be to 2 significant figures because that's what everything else has been given to, and that is a sensible figure. Okay, you can do a common sense check. It is a sensible figure in comparison to the others. Okay, experiment 3, we're asked to calculate the initial rate of the reaction, so we don't even need to rearrange the equation there. We just plug in everything we've already got, easy peasy, and that should give you, what is it for experiment 3? Sorry. 0.26 I've got here, is that right? Sorry, let me just check the marks to have I written that down correctly. 0.26, question 2, yeah, 0.26, right. Sorry, I've got some answers that I previously worked out, I wasn't sure if that was correct. Okay, 0.26, again, I'm going to 2 significant figures here because that reflects the others. And then finally for this one, so similar working out to the one we did for experiment 2. So we're going to say H plus squared equals rate over K times BrO3 minus times Br minus, and when you calculate that, you're then going to square root the answer to that, and that should give you an answer of 0.46, again to 2 significant figures, and that's a sensible answer given the previous concentrations. Okay, So for question C, second series of experiments is carried out to investigate how the rate of reaction varies with temperature, and the results are used to obtain a value for the activation energy. Identical amounts of reagents are mixed at different temps. Time taken for a fixed amount of bromine to be formed is measured at the different temperatures. Oh, right. So, first thing you need to do for part C is to complete the table. This table is easier than the previous table because all you have to do for this value here, so 1 over T, big T, so you're going to say 1 over, so that is 1 divided by 302, and that gives you an answer of, oh, I've missed one here, haven't I? I'll come back to it in a minute. Okay, that gives you an answer of, again, we need to follow suit. I have 3 significant figures, so that gives you 3.31 times 10 to the minus 3. And then this one, so you've got value here for 1 over t, so you're just going to say ln times 1 over t, and that should give you a value, again, to 3 significant figures of 3.30. From memory, having marked this question, the significant figures here are what let people down, which is such a shame. Okay, that is 2 marks is incredibly generous, I would argue, for that question. Okay, now part D is the bit that kind of sends everybody into a wild panic, and it really needn't. Oh, sorry, my tea's gone cold. So, if you are attempting this question, by this point you should be fairly familiar with the Arrhenius equation and its logarithmic version. So we've got here ln k equals minus EA over R times 1 over T plus C1, and it tells you down here C1 and C2, which we'll come across in a minute, are constants. That is basically exactly the same as saying that, which you have come across already, okay? Because this is a constant and this is a constant, okay? And then if you come down here, it says in this experiment, the rate constant K is directly proportional to 1 over T. So we can therefore substitute that for that, okay? And then this is still exactly the same as that. And as I say, if you're attempting these questions, you should have worked your way through the PowerPoint and how to go at plotting a graph and using that graph to calculate a gradient, and then using that gradient to calculate the activation energy. That is what you're going to do here. They've given you a slightly different format with different constants, and that is the aim of that, is to kind of throw you off a bit. All right, but don't let it, because the next step is to plot your graph, and this is where it could throw you off, because you will have learned, hopefully by this point, that you plot ln k on the y-axis against 1 over t on the x-axis, okay, and it actually tells you there that that's the y-axis. And 1 over t, therefore, is going to be the x-axis. Okay, so ordinarily, I'm going to put here ln k equals y-axis, and 1 over t, that's 1 over big T being temperature, equals the x-axis. But this time, instead of ln k is equivalent to ln 1 over little t. Okay, so we just need to find up here, this is going to be our y-axis. It's worth, you know, just label it, why not? And this is going to be our x-axis, okay? Now, the hardest part about these questions, the calculation itself isn't difficult. The hardest part is plotting the graph. It's difficult because it's really time consuming, potentially, and for the number of marks available, you know, you have to kind of really give yourself a cut-off point. If you're struggling to work out what an appropriate scale is after a certain period of time, to be honest, I'd consider just moving on and popping down some workings out, you know, put down the equation rearranged and kind of hope for the best and get on with it, really, because if you are spending 20 minutes on a 6-mark question because you're not very good at drawing graphs, you're going to lose marks elsewhere in the paper that you could definitely have got given enough time. So, you know, you really do need to practice your graphs here. Right, so I cannot stress this enough. Graphs do not have to start at 0. Okay? They do not need, start at 0. They do not need the squiggly line so that you can then jump some figures. You can start at any number, okay? And 9 times out of 10, you will not want to start one of these graphs at 0, because if you do, then everything's going to be bunched up down one end. Your line of best fit is going to be out, your gradient's going to be out, and all subsequent calculations are going to be out. Similarly, if I just turn over, so this is where you're being asked to plot. They've actually done this axis for you. I guess that's to reflect, it's not that it's difficult, it's just to reflect the fact that, you know, these things do take time. And you'll notice here that this starts at what, 3 point, whatever that is. So 3.2, 3.3, 3.4, there's no squiggly line there, okay? Don't need it. So what you need to plot here is ln 1 over little t, and looking at the values that we've got, where is that, for here, it wouldn't be appropriate to start that at 0 because your smallest figure is minus 2.08. Now the other thing to note is they obviously want you here to have a negative y-axis, but sometimes you'll see it, you know, down here and you go up. It doesn't matter particularly so long as it's plotted correctly. The other thing to note is that if you do not use more than half of the grid given to you, and I would aim to use all of it, FYI, but if you use less than half, you immediately lose marking point 1. Now, in the interest of time, because it's not exciting to watch me sketch a graph particularly, and there's a perfectly good one here already. So this is the mark scheme. Okay, so as we said, that was already done for you. They've started at -2, they've gone down to -4, and they've labelled it. That seems like a sensible range to me. You plot nice and precisely with a sharp pencil, and then you draw your line of best fit, and it should be straight. Okay, once you've done that, then you take a gradient, take 2 nice large points, and calculate your gradient, change in y over change in x. And then once you get that, so in fact if I just annotate on here, so the gradient, whatever you calculate the gradient as, and let's just say here, so gradient equals EA minus EA over R, okay? That's what the gradient is equal to. What you are trying to find is just the activation energy, okay? So once you know what that value is, so I think I've calculated it over here. I've calculated a gradient of 6586.21. Right, that is that. I just want that. So I'm going to multiply this by this, and we always know R, and it will tell you in the question, but R equals 8.31. And then the final thing we're going to do is divide that answer by 1,000. Why are we going to divide it by 1,000? Well, because activation energy is measured in kilojoules per mole. We have been working in joules per mole because that's the unit for R, okay? So you're going to divide the answer by 1,000, and if you do that, that comes out at 54.7 kilojoules per mole, and that falls within the accepted range of answers. Now, I mentioned this in the previous question. You can do a common sense check here because it should fall within a range of 40 to 400 kilojoules per mole, which that does. If I hadn't divided it by 1,000, then obviously that answer would be 1,000 times greater than it is. And when I'm doing that common sense check at the end, if I have forgotten to do this step, and you know it happens, you've got a way of remembering, you know, I can't form words today, jogging, thank you, jogging your memory of, I haven't divided by 1,000 because my answer is ridiculous, it doesn't fall in that range. Okay, I'm going to do a video for question 3 as well. It's exactly the same process as question 2. I'm not going to do one for the Edexcel questions because they just follow exactly the same format as the AQA ones, and I'll just ask people to email me individually if they're having any issues, and if it's a widespread problem, then I will do some more. Okay, bye.